You can also use scientific notation to multiply or divide very large or small numbers. Like if I have 3 times 10 to the fifth uh, quantity times 5 times 10 to the 20th. Well, 3 times 5 is pretty easy. That's 15. 10 to the fifth times 10 to the 20th. If only we had just learned a rule about how to multiply things with the same base. It seems like we might have one of those. I think you add the exponents together. 10 to the 25. Now, when you do this, you have to pay attention. Is your a value still good? I notice I have a 15 for an a value, which is bigger than 10. So I have to take one more 10 out of it, make it 1.5, and that makes it just a smidge bigger. So let's try this on example 3 here. Excuse me. I think I need a drink of water. All right. So we're going to evaluate this multiplication of two numbers in scientific notation, and then we're going to express the result both in scientific notation and in standard form. But we're going to start in scientific notation because that's where we're at. So 3.5 times 10 to the negative 3 times 7 times 10 to the 5. Now, I didn't show it before, but what's really happening here is you have 3.5 times 7, the two a values, times 10 to the negative 3 times 10 to the 5. And now you can see a little bit more clearly two numbers with the same base value there. We add the exponents. Negative 3 plus 5 is 2, so I have 10 squared. I don't know why I wrote it equals there. And now all I have to do is have 3.5 times 7, and it should be somewhere in the 20s because 3 times 7 is 20, right? 3.5 times 7, I don't even know what I'm doing. It's 24.5. Again, you'll notice the decimal place is in the wrong spot. It needs to be moved over a smidge more to become 2.45 times 10, and I moved it to the left, so that raises the exponent 1 right there. So that is the answer in scientific notation. In standard notation, all right, the 245, and the first two places for the exponent are taken up with the 4 and the 5, so I just need one more extra one there, and I get 2,450.